Hi everyone, hope you guys are doing okay. This is lesson 2, atoms, molecules, and ions. First, I'm going to give you a brief history of the concept of atoms, the smallest pieces of matter. And then I'm going to describe key experiments that led to the discovery of electrons and to the current nuclear model of the atom. And then I'm going to talk about the modern theory of atomic structure, including the ideas of atomic numbers, mass numbers, and isotopes. We're going to look at molecular weights and how they relate to the mass of individual atoms. And then we will look at the periodic table, where elements are organized in order of increasing atomic number and grouped by similar chemical properties. Atoms can combine to form molecules. We're going to see how the composition of a molecule is represented by empirical and molecular formulas. Atoms can gain or lose electrons to form ions. We're going to see how we can use the periodic table to predict the charge on the ions and thus predict the empirical formula of ionic compounds. By the way, ionic compounds don't have molecular formulas. The systematic way in which substances are named is called nomenclature. We will see how this method is used for naming inorganic compounds. We will introduce some basic ideas of organic chemistry, the chemistry of the element carbon, but you have to go through the notes. I will not include this in the video. Democritus and other Greek philosophers thought that the material universe must be made of tiny indivisible particles they called atomos, meaning uncuttable. Later, Plato and Aristotle formulated the notion that there can be no ultimately indivisible particles. As chemists learned to measure the amount of elements that react with one another, the background was laid for an atomic theory that linked the idea of elements with the idea of atoms. And that theory came from John Dalton. According to him, atoms are the smallest particles of an element that preserve the chemical identity of that element. Dalton's atomic theory involved the following postulates. Each element is composed of very small particles called atoms. Atoms of a given element are identical to one another in mass and other properties. Atoms of one element are different from atoms of all other elements. The atoms of one element cannot be changed into atoms of another element by chemical reaction. That is, atoms are neither created nor destroyed in chemical reactions. This is why alchemistry never works. On the other hand, atoms of one element can be changed into atoms of another element by nuclear reaction. Compounds are formed when atoms of more than one, more than one elements combine together. A given compound always has the same relative number and types of atoms. Now, Dalton reached his conclusion about atoms based on chemical observations in the macroscopic world of the lab. Neither he nor those who followed him had direct evidence for the existence of atoms. Today, we can use powerful instruments to measure the property of individual atoms and even to manipulate these atoms. One such instrument is the scanning tunneling microscope invented by IBM in 1981. Here is how it works. The STM has a metal needle that scans the sample by moving back and forth over it, gathering info about the details of the surface. The needle has a tip that tapers down to a single atom, so the tip can follow the smallest change in the surface of a sample. A computer receives the electrical signal and directs the needle to move up and down to keep the current constant. The path of the needle is recorded, and the computer can display that information as a grayscale image or a topographical map, scientists can also add a color to make the image easier to interpret. So this is 1981. IBM first invented the STM, and here are the two inventors. STM in 1981 revealed for the first time the reconstruction of silicon atoms at the surface. Now, IBM was the first to manipulate individual atoms on the surface using the STM to spell out IBM, the company logo, by placing 35 xenon atoms. This was 1989. Now let's go back to Dalton's time. As scientists begin to develop methods for a more detailed probing of the nature of matter, the atom, which was supposed to be indivisible, began to show a more complex structure. We now know that the atom is composed of still smaller subatomic particles. During the mid-1800s, scientists began to study electrical discharge inside a partially evacuated tubes, which is a partial vacuum tube. When a high voltage was applied to the electrodes, radiation was produced. This radiation is called cathode rays because it originates from the negative electrode or the cathode. Although the rays are invisible themselves, they can be detected because they cause certain materials such as glass or phosphorus to give off light or to fluorescence. And then later experiments showed that the cathode rays are deflected, turned aside by electric or magnetic fields in a way which suggests that they are negatively charged particles. Now, the British scientist J.J. Thomson did a lot of work on this. In 1897, Thomson concluded that cathode rays are streams of negatively charged particles, and he basically discovered what later became known as the electron. Thomson constructed a cathode ray tube having a fluorescent screen at one end so that he could quantitatively measure the effects of electric and magnetic field on that stream of electrons. And this measurement made it possible for Thomson to determine the charge-to-mass ratio of an electron. Once the charge-to-mass ratio of an electron is known, measuring either the charge or the mass of an electron would give the value of the other quantity. In 1909, Robert Millikan of the University of Chicago just did that. So in 1909, Robert Millikan succeeded in measuring the charge of an electron by performing a series of experiments as described here. Small drops of oil, which had picked up extra electrons, were allowed to fall between two charged plates. He then measured how the voltage on the plates affected their rate of fall. His experiments showed that the charge were always multiples of 1.6 times 10 to the minus 19 coulombs, which he deduced as the charge of a single electron. Coulombs, by the way, is the unit for electric charge. He then calculated the mass of the electron by using Thomson's charge-to-mass ratio, and his results agree well with the presently accepted value for the mass of the electron, which is 9.1 times 10 to the minus 28 gram. This is 2,000 times smaller than the mass of a proton. In 1896, the French scientist Henri Becquerel was studying a uranium compound when he discovered that it spontaneously gives off high energy radiation. This spontaneous emission of radiation is called radioactivity. He asked Marie Curie and her husband Pierre to isolate the radioactive components of the compound. Pierre later died in a freaky road accident. Widowed, Curie went on to get a second Nobel Prize in chemistry for discovering another element, radium. She later died of leukemia because of her extensive work with radioactive material. A further study of the nature of radioactivity by the British scientist Ernst Rutherford revealed three types of radiation: alpha, beta, and gamma radiation. Alpha particles have a +2 charge. Basically, they are helium ions. Beta particles are high-speed electrons. Gamma radiation is high-energy radiation similar to X-rays. It does not consist of particles and have no charge. So with the growing evidence that the atom is composed of smaller particles, now the question is how these particles fit together. During the early 1900s, Thomson reasoned that because electrons contribute to only a very small fraction of the mass of an atom, they probably were responsible for a very small fraction of the atom's size. And he proposed that the atom consisted of a uniform positive sphere of matter in which the electrons were embedded. In 1910, Rutherford and several others performed an experiment that disproved Thomson's model.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Later experiments led to the further discovery of both protons and neutrons. So just to give you a summary, atoms are basic building blocks of matter. They are the smallest units of an element that can combine with other elements. Atoms are composed of even smaller particles called subatomic particles, some of which are charged. We have considered some of the important experiments that led to the discovery and characterization of subatomic particles. Thomson's experiments with the cathode rays in magnetic and electric fields led to the discovery of electrons and allowed its charge-to-mass ratio to be determined. Millikan's oil drop experiment determined the charge of the electron. Becquerel's discovery of radioactivity gave further evidence that the atom has a substructure. Rutherford's study of how thin metal foils scatter alpha particles showed that the atom has a dense, positively charged nucleus. Since the time of Rutherford, physicists have learned much more about the composition of atomic nuclei. Now the list of particles that make up nuclei has grown and continues to increase. As chemists, however, we can take a very simple view of the atom because only three subatomic particles, the proton, a neutron, and electron, have importance on chemical behavior. The charge of an electron is minus 1.6 times 10 to the minus 19 coulomb. The charge of a proton is 1.6 times 10 to the minus 19 coulomb. The quantity 1.6 times 10 to the minus 19 coulomb is called the electronic charge. For convenience, the charge of atomic and subatomic particles are usually expressed as multiples of this charge instead of coulombs. So the charge of the electron is minus 1, and the charge of a proton is plus 1, and neutrons are uncharged. And every atom has an equal number of electrons and protons, so atoms have no overall electrical charge. Atoms have extremely small mass because it's not convenient to express such small mass in grams. So we use instead the atomic mass unit, or AMU. 1 AMU equals 1.66 times 10 to the minus 24 gram. A proton and neutron have about the same mass. A proton has a mass of 1.0073 AMU, a neutron 1.0087 AMU, and an electron is about 2,000 times less massive. And atoms are also very small. An easy length unit we use to express atomic dimension is the an angstrom, or 10 to the minus 10 meter. The diameter of an atomic nuclei is about 10 to the minus 4 angstrom. Imagine if the hydrogen atom were as large as a football stadium, and the nucleus would be the size of a very small marble. Because the tiny nucleus carries most of the mass in such a small volume, it has a very high density. The number of protons in the nucleus of an atom of any particular element is called that element's atomic number. Because an atom has no overall electrical charge, its number of electrons must equal the number of protons. For example, all atoms of carbon have 6 protons and 6 electrons. Atoms of a given element, however, can differ in the number of neutrons they have, and consequently differ in mass. For example, most atoms of carbon have 6 neutrons, but some have more and some have less. The symbol C12, carbon 12, represents the carbon atom containing 6 protons and 6 neutrons. This subscript represents the atomic number. This superscript represents the mass number, or the total number of protons plus neutrons. Atoms having the same atomic number but different mass number, that is, atoms with the same number of protons but different number of neutrons, are called an isotope of one another. Several isotopes of carbon are listed here. As we noted earlier, it's convenient to use the atomic mass unit when dealing with a very small mass. The AMU is currently defined by assigning exactly 12 AMU to one atom of the carbon-12 isotope of carbon. So 1 AMU equals 1.66 times 10 to the minus 24 gram, or 1 gram equals 6.02 times 10 to the minus 24 AMU. In these units, a hydrogen-1 atom has a mass of 1.0078 AMU, and oxygen-16 atom has a mass of 15.9949 AMU. Most elements occur in nature as mixtures of various isotopes. We can determine the average atomic mass of an element by using the mass of its various isotopes and their relative abundance. For example, naturally occurring carbon is composed of 98.93% carbon-12 and 1.07% carbon-13. We can calculate the average atomic mass, aka atomic weight of carbon, from the relative abundance of each isotope and the mass of that isotope. So this is the percentage abundance of this particular isotope, which has this mass, and this is the percent abundance of the other isotope, and this gives you the average atomic mass of carbon. The average atomic mass of each element is also known as its atomic weight, and the atomic weights of all the elements are listed in the periodic table. Now, the most direct and accurate method for determining atomic and molecular weight is using the mass spectrometer. A gaseous sample is introduced at point A and then bombarded by a stream of high-energy electrons at point B, which produce +1 charged particles. These +1 charged particles are accelerated toward a negatively charged wire grid at point C. After they pass the grid, they encounter these two slits, which allow only a narrow beam of particles to pass. This beam then passes between the poles of a magnet, which deflects the particle. For particles having the same charge, the amount of deflection depends on mass. The more massive it is, the less the deflection. The particles are thereby separated according to their mass. By changing the strength of the magnetic field or the accelerating voltage on this negatively charged grid, charged particles of different mass can be selected to enter the slit and to reach the detector. A graph of the intensity of the detector signal versus the atomic mass is called a mass spectrum. This figure shows the mass spectrum of chlorine atoms, revealing the presence of two isotopes, these two here, and the relative abundance of these two isotopes can be determined from the relative intensity of their signals. And now we know the atomic mass and the relative abundance of all the isotopes, and we can determine the atomic weight of an element. Dalton's atomic theory set the stage for a rapid growth in chemical experiments during the early 1800s. As the body of chemical observations grew and the list of known elements expanded, attempts were made to find regular patterns in chemical behavior. These efforts culminated in the development of the periodic table in 1869. In the periodic table, elements are arranged in order of increasing atomic numbers, with elements having similar properties placed in vertical columns. For each element, the atomic number and the atomic symbol are given. And in some periodic table, the atomic weight of an element is also given. The horizontal rows are called periods. The first period has only two elements, hydrogen and helium. The second and the third periods, which begin with lithium and sodium, have 8 elements. The fourth and the fifth periods have 18 elements. The sixth has 32, but for it to fit on a page, 14 of these elements, those from atomic number 57 to 70, are placed at the bottom. The seventh, or the last period, is incomplete. It also has 14 of its members placed at the bottom. The vertical columns are called groups, and there are 3 ways to label them. And we show 2 of them here. And the top set of labels with the A and B is used in North America. Sometimes you will see Roman numerals used. The IUPAC proposed convention to label groups from 1 through 18 with no A and B designations. We are going to use the North America convention. And elements in the same group often have similarities in physical and chemical properties. For example, the coinage metals, the copper, silver, and gold, all belong to group 1b. These metals are used to make coins. And many other groups also have names, as you see here. The group 1A elements are called alkaline metal. Elements in group 2A are called the alkaline earth metals. Elements, those in group 7A are called the halogens. The group 8A are the noble gas. Now we are going to learn later that elements in the same group have similar properties because they have the same arrangement of electrons. Except for hydrogen, all the elements on the left side and in the middle are metallic elements or metals. So the majority of the elements are metals. They all share characteristic properties like luster and high electrical and heat conductivity. All metals except mercury are solids at room temperature, and the metals are separated from the non-metallic elements or the non-metals by a zigzag line that runs from boron to astatine. At room temperature, some of the non-metals are gaseous, some are solids, and one is liquid. non-metals in general differ from the metals in appearance and in other physical properties. Here are some familiar examples of metals and non-metals. Here you have sulfur. These are a yellow powder. This is iodine. This is a bromine vapor in a vial. This is a carbon in 3 different forms, as graphite in a pencil, as charcoal, or carbon in the form of diamond. And then here are the metals: aluminum wrench, copper pipe, lead, gold, silver coins. Many of the elements on this zigzag line that separates metals from non-metals have properties in between the metals and non-metals. These elements are called metalloids. Even though the atom is the smallest representative sample of an element, only the noble gas elements are normally found in nature as isolated atoms. Most matter is composed of either molecules or ions. We are going to look at molecules here, and ions next. A molecule is basically a combination of 2 or more atoms joined together. Many elements are found in nature as molecules made of 2 or more of the same type of atoms combined together. Or for example, oxygen. The oxygen in air consists of molecules made of 2 oxygen atoms. We represent this molecular form of oxygen by the chemical formula O2. The subscript tells us there are 2 oxygen atoms present in each molecule. A molecule that is made up of 2 atoms is called a diatomic molecule. An oxygen also exists in another molecular form known as ozone. Even though normal oxygen O2 and ozone, or O3, are both composed of only oxygen atoms, they are very different in their physical and chemical properties. For example, oxygen is essential for life, but ozone, O3, is toxic. Oxygen is odorless, and ozone has a sharp and pungent smell. The elements that normally occur as diatomic molecules are hydrogen, nitrogen, oxygen, and the halogens. When we speak of the substance hydrogen, we mean H2. When we speak of oxygen, nitrogen, or any of the halogen, we are referring to O2, N2, F2, and so on and so on. Compounds that are composed of molecules have more than one type of atom and are thus called molecular compounds. For example, a molecule of water consists of 2 hydrogen atoms and 1 oxygen atom, and is therefore represented by the chemical formula H2O. Another compound composed of these very same elements, but in a different proportion, is hydrogen peroxide, H2O2. The properties of hydrogen peroxide are very different from the properties of water. This figure shows several common molecules. Note how the composition of each compound is given by its chemical formula. And also note that these substances are composed only of non-metallic elements. As a matter of fact, most molecular substances contain only non-metals. Now, chemical formulas that indicate the actual number and types of atoms in a molecule are called molecular formulas. As you see here in this figure, chemical formulas that give only the relative number of atoms of each type are called empirical formulas. The subscripts in an empirical formula are always the smallest possible whole number ratios. For example, the molecular formula for hydrogen peroxide is H2O2, and its empirical formula is HO. So whenever we know the molecular formula of a compound, we can determine its empirical formula, but not the other way around. So why chemists bother with empirical formulas? Well, as we are going to see later, certain methods of analyzing substances lead to the empirical formula only. Once the empirical formula is known, additional experiments can allow us to convert the empirical formula to the molecular formula. The molecular formula of a substance tells us the composition of the substance, but doesn't tell us how the atoms come together to form the molecule. The structural formula of a substance tells us which atoms are attached to which. For example, the structural formula for H2O, hydrogen peroxide, and methane are shown here. The lines represent the bonds holding the atoms together. A structural formula can also be written as a perspective drawing to give you a sense of three-dimensional shape. Scientists also rely on various models to help visualize molecules. The ball and the stick model show atoms as spheres and the bonds as sticks. The sphere can be of the same size, or they can have a different size, reflecting the size of the atom. A space-filling model depicts what the molecule would look like if the atoms were scaled up in size. These models show the relative size of the atom, but the angle between the atoms are often very difficult to see. So this is the disadvantage of the space-filling model. An atom's nucleus is unchanged by chemical process, but some atoms can readily gain or lose electrons. If electrons are removed from or added to a neutral atom, a charged particle called ion is formed. An ion with a positive charge is called a cation. A negatively charged ion is an anion. For example, a sodium atom has 11 protons and 11 electrons. Now this atom easily loses 1 electrons, and the resulting cation has 11 protons and 10 electrons. The net charge of an ion is represented by a superscript. A chlorine atom has 17 protons and 17 electrons, and this atom easily gains electron in a chemical reaction, producing a chloride ion. In general, metal atoms tend to lose electrons to form cations, and non-metal atoms tend to gain electrons to form anions. And in addition to these simple ions like sodium ions and chloride ions, there are polyatomic ions, such as the ammonium ion, the sulfate ion. These ions consist of atoms joined together as in a molecule, but they have a positive or negative charge. We are going to talk about polyatomic ions later. Note that the chemical properties of the ions are very different from the chemical properties of the atoms from which they are derived.